every parameter. You might have any underlying model here. So, if we are computing gradient with respect to theta, this is the parameter, then you can optimize parameter theta, right. You can get updated values for parameter theta. Xi is the input, you know that is fixed, it is given to you. So, if you compute the gradient with respect to xi, it will tell you that how sensitive your loss function is with respect to the input rate of change, right. So, if we compute the gradient with respect to xi, so this will tell us that which feature is important, right, for which this loss function is basically changing, or you can say varies. So, if you change the values of xi, your loss function will change. So, using gradient approach, we try to find out the change. So, only the difference that we are going to discuss in the attack system, we will try to induce noise in the data such that it is not basically visible or perceivable by the humans, but model perceives it and it basically changes its decision accordingly. So, one is basically the way, suppose I say that we try to optimize by assuming that xi is a parameter, we try to minimize the loss with respect to xi. Then again we have to process the same thing, right. So, we have to follow the similar approach here. So, here one for gradient descent approaches, please see here. So, the symbol will be minus, maybe I can update it here in a minute. So, it must be minus. Okay. So, that is the gradient descent update, but at the same time if we want to attack on this system, right. So, we have to basically update the input, right. Just one equation I am just writing, copying it and writing it again. Maybe we can make it little small, and this theta I am just going to replace with x. Of course, it might remain same. So, this theta is x. Eta now I am just going to replace with epsilon. So, epsilon, very small quantity. This sign is now I am going to write plus. This L with respect to x. What is x omega? What is the problem? Right, yeah. And this xt, maybe I can just write somehow dash also. And this is also, maybe leave it. Okay, we will discuss this in a moment. So, in gradient descent what we do? So, we update the parameter theta at tth iteration by using this equation, by moving in the direction, negative direction of the gradient or opposite direction of the gradient and making a small step. So, that is the eta learning rate, you know, yesterday we discussed in the optimization, that is learning rate, right, you know that. So, if you change it, your optimization or convergence basically varies, and there might be possibility that for a specific value of learning rate you might not converge, right. So, that is why we have different variants like momentum, adaptive gradient, RMS prop and time optimization algorithms, and there are many more other approaches also. So, we are not going much into that. So, this is the way we train the model, we learn the model, we learn the good model, we update the parameters and finally we get the good values of the parameters. Now, the question comes at the second one, the equation that I have written right now. We are saying that x t, we want to design a x dash for a particular example, let Tth is a sample x t. We want to design x dash, right, such that this is instead of moving in the negative direction of the gradient, please see the change. Instead moving in the negative direction of gradient, we try to increase the loss. So, decision will be changed when you are able to increase the loss, please note down. If your loss is minimized, then model will going to give you the correct decision. But somehow if you try to basically increase the loss value or loss values, right. So, there is a possibility that decision of the model should change. So, the idea is here we design a sample. So, instead of parameter, so just take one sample, maybe t minus 1 is the previous sample or one sample you can say, original sample you can say. You just add the gradient of, you can say, loss with respect to this sample or input features that you have. So, this second term gradient of loss with respect to this input feature will tell you how sensitive your model is corresponding to certain parameter, certain x t minus 1, and you just make a very tiny small step, epsilon must be very small, and you just get this sample x dash t. You will get x if x t minus 1 is an image or text sentence or whatever you say. So, x dash t is also an image, but in that image what we have added? So, we have added this thing, right. So, we have computed the gradient, the feature which has a higher value. So, it will be basically affected much, epsilon is a very small perturbation, right. You add it, you will get a corrupted sample, or you can say fake sample, or you can say adversarial sample, right. And you just just provide this data, this spurious sample to the model, and your model will be fooled. So, suppose x t minus 1, or you can say this previous sample or original sample has a class 1, then this x dash might give you different class, maybe class 0 or class minus 1, something like that. So, that is the attack. This attack is called gradient based attack, you can call it fast gradient method to attack on the system. You just design the sample, but instead, because here you can say that this is a little bit tricky to identify, many times gradient computation is costlier, it might be many things, but suppose somehow we are able to get the sign of this gradient, just to get the sign whether this is positive or negative. You know that if the sign is positive and gradient for gradient with respect to parameter, so sign positive means, so when will you get gradient positive? If slope is less than 90 degree, right, you have tan theta positive. If it is beyond 90 degree, it is tan theta negative, your slope is, your gradient is negative. So, if you are at the right side of the minima, right, you have a convex function, right. Okay. If you are at the right side of the minima, so any point on the curve if you take here, so gradient is positive, right side of the minima, and if you are at the left side of the minima, left side on this curve, so your gradient will be negative, because theta becomes more than 90. Is it clear? You can see here. So, if you can compute gradient here, so what is the direction? You just On axis you just see that what is the angle it made. At this point, if you say the direction will be like this, you just see here, so the angle will be 90 plus, right. So if the gradient direction is you can say gradient value is sign is positive. So in order to minimize the function, we have to reduce something from the current value in the parameter that you have. So we just multiply with a small step size, that is called learning rate, and we try to move in the negative direction of the axis, right, if your gradient is positive. If gradient is negative, the parameter value gets increased, right, because you have to move in the direction of the axis. Because in order to minimize, we have to move to the into the opposite direction of the gradient. So if gradient is positive, it means you have to reduce something from the data point or the parameter. If gradient is negative, it means you have to add it. Add means moving in the direction of the axis, whatever you have here, and reduction means you are reducing the value and you are moving in the opposite direction of the axis. So if we plot this one with respect to input data. So instead of parameter, suppose it is this W represents the input feature, so some feature. So we want to basically confuse the model. So instead of minimizing the loss, adversary aim will be increase the loss. So we will try to generate a sample such that it try to increase the loss, right, loss value. So we will move in the direction of the gradient. We will move in the direction of the gradient. So if it is gradient is positive, so we add something in the value so that it loss becomes high. If it is negative, we subtract something so that it becomes even more, loss becomes more high on those values. So that's the idea here. And this thing we will do in the attack design. So see here, one thing I can just tell you, suppose you are not able to compute this gradient, let you have a very complex function. So loss is a very complex function, but somehow you are able to get the sign, whether gradient is either you are in the left side of the minima or optima, or you are at the right side of the optima. If you know that sign. So getting sign of the gradient is very easy, right. So what you do, just get a sign instead of computing the whole gradient, just get the sign. And if your gradient is positive, so in the data you just add something, very small value you just add. If gradient is negative, you just subtract something, so that loss with respect to that sample becomes huge. This method is called FGSM, fast gradient sign method, right. So only in the gradient step that we do, and we have to compute with respect to the feature vector, gradient with respect to the feature instead of parameter. Here I am just giving the idea. So this equation is, instead of writing this one, you just say that okay, I am just copying it again. Maybe I am just writing in more way, more elegant way. You can say original. I am just writing. You can write corrupted or whatever you say. So I am just little bit rewriting. So I am just for timing removing this omega. Let omega equal to 1, by the way. What should I write here? Original, right? Yes. And this equation I am just going to rewrite again. I am just writing here, so little here and there you have to just think. So, instead of computing this whole thing, so what you do? You just say this sign. And, maybe we can give one space. Okay. So, what we are doing? So, epsilon is a very small perturbation, very small noise, you can say whatever you say. So, which one is basically faster? The second one, of course. We do not need to basically process the gradient, just sign is sufficient for us. If sign is negative, we will subtract something from the input, and if sign is positive, we add something. And this is the inverse phenomena. So, this basically process basically try to maximize the loss, right, because we are moving in the direction of the gradient, and the direction of the gradient is defined by the direction in which loss function basically increases, or you can say the function objective function basically increases. So, that direction is called the positive direction of the gradient. Okay. So, just say here, so the second one is called FGSM method. So, we will demonstrate it right in a moment. Then another one is, many times you do not know that actual value, maybe what might be the epsilon and others. So, you can just make a iterative method, you just have a for loop here. So, every time you just put a small noise until you get a perturbed image, X perturbed, such that it basically fools the model. So, epsilon will be a certain range, you just put a allowable range and you just do it, right. Just try to get a sample, or you can say fix, you can just try to get a fake sample using the original image. So, here one important thing is that original data is required for this attack. You should know that what is the data basically for which it works well. So, you have to just perturb the data, and this X perturb, the what is the criteria for this X perturb? So, X, so as a human eye or as a human, you should not be able to make much difference. So, it means that X perturb minus this X original, if you compute the difference, so this difference must be small and must be basically negligible in some sense, that human should not perceive it. So, that will define the second quantity, right. So, suppose I say that X perturb minus X original. So, what will happen? So, you have epsilon times sign. So, this difference that you just see that it should be very small, so that as a human, as a basically you can say expert or the person, you should not be able to perceive, but model, and accordingly the model should not be able to get it, and it changes the decision. As a human, we say that the image belongs to cat, but machine says it is dog. Though your model is correct, but because it is sensitive towards certain feature, and we have added this amount, very small amount to that feature value, and it changes the decision, right. So, FGSM. Another one is iterative method, you just keep on adding it until you get the image which basically fools the model. So, we have two things, one is basically you just limit this epsilon, you say that okay, we cannot put arbitrary epsilon, you just say that okay, this is the allowed range. So, every time you just do it, you just see that whether the update that we are making it is in the bound or not. So, you just say that feasible set. So, allowable set, you just try to map, try to project your data perturbed image to that particular set. we call it projected gradient method. So, we will animate today. So, what is projected gradient descent and gradient descent, then the same criteria we have used here. So, just this change this noise that we are adding, we have to just map into this some certain feasible range that humans cannot perceive, right. So, we call it projected gradient descent. Just you repeat, you just make the iterations for loop and you just keep on doing it until you get it, that is called basic iterative method, BIM. And this is a very popular method we will demonstrate today. Okay. So, I think this story you can see here, we have many things here. So, we have discussed maybe many things we will discuss in the tomorrow session. So, what the idea is, you just see, so you have a original image. So, this is some small perturbation that we are going to add. So, what is that? That is epsilon into the sign of the gradient. Right. Epsilon is a random vector, right. You can say epsilon is a very small positive noise, you can say, you add it. So, originally it is you can see that what is the class here, original class might be panda or something, so some maybe some object here, but when you add this noise it might be classified as different class, right. So, this is the idea here. So, you can see here the same way you have a school bus, you add certain little perturbation, and perturbation is just noise. You can see the what is the output. So, output you can say that human is able to identify this is a school bus, but model is now trying to say ostrich, right. So, this is fast gradient sign method. You can say treat a model as a linear model here or basically black box setting. So, then take a step into the direction of the gradient, and in so this is the way we are doing it, right. You just see. So, generate the adversarial sample and try to fool the model. This is the another method, we call it iterative fast gradient sign method, or you can call it basic iterative method. So, instead of just keeping it designing epsilon in one step only, you just keep on iterating. You just start with the sample and you just every iteration you just add a small noise such that it try to basically fool the model. So, you just keep on doing it, you will get the adversarial image like this, and you will see that your classifier will be fooled. So, this can be used to assess the model robustness as well. Then we have another method, you can call it projected gradient descent method. So, what you do, whatever change we are making in the fast gradient, you can say that might go here and there. So, just try to clip, you just put a certain upper bound and lower bound on the noise. So, how much perturbation you are going to allow. So, you can say it is a circular region. So, only up to certain extent we want to allow the perturbation. So, just clip it. So, this is basically, suppose I say that you have a variable x and it must have value between let -3 to +3, and somehow you are updating the value of x and somewhere you got -4. So, -4 is not in the allowed range, right. So, you have to clip it to -3. Likewise, if you have value more than 3, you have to clip it to 3, right. So, you have to project your data into this allowable range. So, that is the clipping. Clip is one approach. You might have some other approaches which can map to the feasible set that is allowable here, and you will get the adversarial sample. And most of the time you can see that it is better in practice. You can design, you can attack most of the system using this attack. Okay. So, taxonomy of adversarial attacks are there. So, I am just going to the demonstration, then we will discuss maybe in tomorrow session, right. So, we can, I am just sharing the codes, right, do not worry, you just practice, right. Okay. So, we have to So, this optimization I think everyone knows, right. So, today I am just going to share you two models, one is this one. So, by the way, in this code, the first code FGSM code, we have also plotted this VC dimensions. You can just check those as well. So, FGSM basic iterative method, and most of them are on MNIST data, digit recognition data, and PGD. You just check it. This one is basically Trojan attack. I am just sharing this file as well. You will find many code. So, they are different in some sense from one and another. So, you just see that what you can understand from those codes. This is neural network as a memory scrap, memory dump. Right. You just start using the first one. So, what should I say? Yes. So, first step in this code what we have, so you have to train a model. So, we want to just use this attack after the training. So, once you have model, someone has given you the model, some app you have, and it is stored as a cloud on cloud. So, machine learning as a service, right. So, you do not have access to the model parameters, only what you have, you can just provide input, you will get output. And you know that if you have input and output, right, you can compute the gradient of output with respect to input. You just create a vector, just try to approximate this change. That will give you the sign of the gradient very quickly. Fight saying connector. Okay, GPU से connect करेंगे, just a minute. इसका तो हटा हुआ है. Okay, so we don't use GPU. So why it's saying GPU? Reconnect. So it's saying that pay as you go, but I don't have money. Okay. This file is shared with all of you, right. So we are going to execute. So we are just training a model and basically saving and training a model. So just you see, we are loading a MNIST data, right. You see, right. So likewise, you can have any other data. So this is basically digit recognition data. So it contains the images of digits 0 to 9, right. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes 0 to 9. So given any digit, you have to classify whether it belongs to 0, 1, 2, 3 or like that. So just execute it. It might take some time based on the number of iteration, because it is little bigger data. Just keep on doing, all of you. Oh, क्या कह रहा है? it is trying to download. Oh. So, here you can see that we are using a neural network, simple neural network and which has one convolutional layer, CNN layer first, CNN layer second, right. So, in the first convolution layer, the filter that we have, filter size is 3 cross 3, number of filters we have 16. So, in convolution to you know that the input dimension becomes 16, right. So, number of kernels we have 32, kernel size is 3 cross 3, padding we are using as 1. So, if you know computer vision, so convolution operation, you know padding, you know stride, right, and you know the operation, convolution operation. Then we are using basically max pooling here to reduce the feature map size, and then we have a linear dense layer. FC1 is fully connected layer or dense layers, and we have 2 fully connected layers, and this is the last layer you can say here. So, where you can say we have input from here, you will get 128 dimension output from FC1, FC2 uses 128 dimension input, and it provides output of 10 dimensions or 10 values it provides. So, the value which is high, you can say the input is classified to that class. And then activation for this one is basically ReLU activation, rectified linear unit as a, you can use sigmoid also, so it depends at what you are using, right. So, this is the simple CNN architecture, you can just do it. So, this is the forward pass, then accordingly if you compute the gradient and all other things it will turn, right. You just see here. So, you have a model, simple CNN model, cross entropy we are using as a loss function, ADEM we are using as a optimizer here, you just see here. So, we have already discussed all these things, right. ADEM we have already discussed, right. Only cross entropy we have not discussed. So, cross entropy is a loss when you use the discrete output, right. Maybe we will discuss it tomorrow, right. So, do not worry when we will discuss the GIAN. You just remind me, right. So, we will discuss that entropy loss as well. So, number of iterations, you can say number of epochs are 5. So, just execute train this model for 5 epochs, because we have a large data samples. So, 60,000 samples in the training, 60,000 images, and 10,000 images are in testing data. So, that is why it might take some time, it is executed. Okay. So, we have saved the model, and the name of the model is amnist CNN.pth. So, this is the model, we have saved the model. Now, the next step is, so this model now now I will share you this model to you. Okay. Yes. You might increase. So, just for illustration I am just doing here. If you increase the number of iteration, of course, it might give you the minimize the loss, but we will discuss few more things. So, it is not very easy, because the neural network that we are going to train here, the loss function is not convex with respect to all the parameters that we have. So, only the model by design we fix convexity fixing is done through the last layer. So, only the parameter that belongs to the last layer, the loss function is convex, and with respect to other parameters, if you have nonlinear activations, the loss is not going to be convex. So, see there are two things, maybe convexity will discuss, maybe after demonstration we will discuss that. Okay. So, also please note down this one, convexity will show the convexity, what is convex function and what are the non-convex function. So, we will discuss that. And then we just tell you that the loss function that we are using in complex neural network architectures, they are designed by keeping the last layer in the mind, the parameters in the last layer in the mind, not with the other parameters. So, that is why we have a highly non-convex function. So, loss function with respect to other parameter is non-convex. So, non-convex means you might have many local minima, many local traps you have, right. So, many times if you execute this algorithm many time, you will get different loss, different accuracies. The reason is that if you change ADAM optimizer with some other optimizer, you will get different loss. So, if it is convex function, then it has only one minima. So, if you have little basically trick about how to choose the learning rate, how to choose the optimization function, you will always reach to the minima or near the minima, but in practice it is not here. So, neural network loss function that we have, it is not convex with respect to all the parameters. So, that is why somehow we are using convex optimization algorithms. Okay. So, we are somehow using convex optimization algorithm, starting stochastic gradient descent, right, main gradient descent, batch gradient descent, momentum based gradient descent, right, adaptive gradient, RMS prop, ADAM optimization. All are algorithms which basically minimizes the loss function of convex loss, right, but our loss is not convex with respect to all the parameters. So, of course, they are not going to give you the optimal results, right, but in practice we try many improvements in the algorithms, and in practice it works. So, that is the challenge here. So, if you increase the number of iterations, number of epochs, you might get basically good accuracy, you might be able to minimize the loss. Many times it starts increasing. So, whenever it starts increasing, it means that the parameter weights is again now going in another direction. So, your loss is, it was you touch minimizing, right, up to some certain extent it is basically loss is reduced, but later on if you increase iteration it starts increasing. So, that is why we have one every package has one option, we call it early stopping. So, when you see that loss is not going to improve, it is now badly increasing, or you can say it started increasing, you just stop the learning, right. So, early stopping is one of the criteria that you can use. You can have many iterations, but do the early stopping that might basically solve the problem of this, right. So, here we have a model, we have shared the model. Now, I will share that model to all of you. So, you just assume that I have shared you. So, the next block of code is going to design attack for this. Okay, so model saved successfully, good. So, now just see what is the we have to know the architecture, otherwise you cannot load the model. So, this is the architecture. So, we have written here data set, we are just downloading the same one. So, just see here. So, we are loading the model. So, MNIST, so this model we are loading here. So, just write the path, basically path of that model file, and you just put it here, and then define this FGSM attack. What is the FGSM attack? You just provide input, the original image, original data, original input, epsilon that how much perturbation, how much step size, how much basically noise you want to add, and gradient with respect to input data point, right, input image, right, that you have. Just provide this one. So, exactly you just provide the sign, by the way. So, here you can by the way you can provide gradient as basically sign, generally we are interested, you just see. So, the first step perturb image is image plus epsilon into sign of the gradient with respect to the input. Is it clear? So, perturb image you can say just make it of different size. So, you can say return the perturb image. So, you call this function, it will give you fake image, or you can say dorsal image, dorsal sample. Epsilon is 0.2 we are using here in this code. You just see, you just do it, and test it, and you just see that FGSM attack perturb data, you can plot it and you can generate accordingly. You just see that here. So, original class level for this is 2. Can you see here? So, original label that for which the correct the model is basically correctly predicting it, it is 2. So, if you add some noise in this, right, that is 0.2, epsilon is 0.2 in our case, it is classified as 1. So, but it is, if as a human you will look into, so is it 1 or 2? 2, right. So, this is FGSM attack. You can change epsilon and you just see that how it is happening. Then you can see here we have all the attacks, right, FGSM, BIM and PGD. So, projected gradient descent. So, in projected gradient I am just giving you the idea. So, you just see. So, in BIM what we are doing, so you have a basically iterations, you just define the iteration, you just see. So, every time what you do, just do a small perturbation, just get the image, get the image, get the image, you just see here, you just keep on doing up to certain iterations. Compute the loss, you just see here. So, this is output the model, you just get the perturbed image, loss equal to this one, then you just keep on doing it until it basically try to maximize the loss, and then that image you just provide for the perturbed image you generate from here, return it and test it for the testing. So, PGD attack is simply the change that you have here. You have to basically clip it. It should not go up to in VIM what is the change? In VIM it might be anything. So, it might be very bad loss, large noise might be there, but here it should not be. So, in basically projected gradient, so every time you have to project it into the range, what is admissible range, or you can say feasible set. So, that is the idea in PGD attack, right. So, just clamp it, you just see. So, clamp is basically you have to make the values clamp with lower bound and upper boundaries. So, it should not go beyond that. So, just perform this attack. So, we have iterations and all these things you can just change, and accordingly you just see that what is happening. Which attack is better, you can just identify. Can you see here? So, original class for this image is 3. Using FGSM, it says 3. So, FGSM attack is not successful here, but if you apply BIM, basic iterative method or iterative FGSM, it says this is 9. Can you see the image, perturb image? Human says 3, right? Bill says 3, but your model now saying that it is 9. PGD also saying 9, right? Because PGD is just little advanced of version of VIM. So, where we are just clipping the boundaries. Yeah, please. Okay. So, is it clear to everyone? So, just keep on adding the noise and you just see that when this is corrupted. So, just change the this perturbation value epsilon, you just change to high value, you will see that human might not be able to identify. So, then you cannot say anything about the machine, right. So, we want this epsilon very small, that humans should say that this is 3, but machine is not able to get it, right. So, this is defense against these one. So, what generally we do in order to defend, right, maybe. So, so it is basically the code is running for all the samples we are doing basically for many samples in order to see that what is the original accuracy, what is the, if we attack, what is the accuracy using FGSM, BIM and PGD, then we will try to put defense strategy. So, what is the defense strategy? So, during the training process, we will consider these adversarial samples. So, we will try to augment our data, right. So, using these adversarial samples, we generate adversarial sample. We know that people will do FGSM attack on my model. they can do PGD attack or BIM attack. So, we will try to make a model which is basically defensive against these attacks up to certain extent. So, what we do? So, we design network samples keeping in mind that maximum epsilon that we can allow. So, that whenever you go beyond that epsilon, you add more noise, even human is not able to understand what is there, that image. But until the human is saying that this is the image, original image. So, up to that level you add the noise, generate the universal samples, put in the training data, train your model, then send your model to the for deployment, and people will try to attack, and if they need more large value of epsilon, you can say they want to perturb it more, so that humans are not able to identify, then I think that the purpose of attack is lost, right. So, people will say that nothing is visible, right. So, even I can't say anything. So, how can I say that model will say anything, right. So, you can discard it, but for these things I think these are the acceptable range, human can directly tell that this is 3, this is 1, this is 2. So, we will use the same thing. So, we will use these attacks to generate the universal samples, or we can use this strategy during the training process, during the learning process. So, just generate these samples, just either fine tune your model. If you have large model, you try to fine tune with this additional data, right, or you can retrain your model including these samples. So, your model will be robust. So, we have other parts. So, here it is executed by the way. So, you can say that what is the attack accuracy. So, FGSM attack success rate is 64.43. So, it is out of many samples, 60,000, or you can say in test data 10,000 samples or many samples, it is able to achieve 64.43% of attack accuracy, means it is able to mislead the model for 64.43 samples percent of samples, right. BIM attack is successful around 97.52, right. So, around 97% samples are attack prone. You can come up with a basically adversarial sample you can generate, such that they can fool the model, they can classify the data into different classes. So, this is the successful attack success rate, right. So, which one has best one? BIM and PGD, right. So, now we will design the model, so that it so these attacks are not so this much successful. So, of course, attack is possible, because at the same time we have to make our model to do correct prediction for the real data as well, right. So, we cannot train the data on these adversarial samples only, otherwise what will happen, your model will not be able to identify or diagnose correct samples, even clean samples as well. So, we have to somehow compromise on this, and so this module, this is basically doing the defense, and here you can say this is the attack, original digit is 9, FGSM is 7, saying 7, BIM is also saying 7, PGD is 7. For this data, all the attacks are successful, by the way, right, for this sample. So, but we are computing we are basically training it, and we'll see that what will happen after a defense mechanism, right. So, it will take some time to retrain and execute, right. Even you can fine tune, right. So, when is the break, I think? So, it yeah, 10 minutes, right, 3:30. Yes. So, can you see here the attack accuracy is now? Earlier you know that what was the attack accuracy, 64% around it was for the FGSM, 97% for BIM and PGD, right. Now we have trained model robustly. So, we included some adversarial samples during the training process. Can you see that defense accuracy over against FGSM attack? So, against FGSM attack defense accuracy is, so this attack accuracy is 30%. So, earlier it was 64, but now it is reduced to 30%, around 34% be reduced in the attack possibility, right. So, for BIM attack from 97 it is reduced to 42, but for PGD defense, defending PGD, so the attack possibility is 56%. So, from 97 it is 56, but can you say here which one is the more stronger attack? PGD, because we are not able to reduce much, right, using our defense strategy, whatever strategy we have made. So, that is including this adversarial sample during the training process. Even if you use, include more samples, you might reduce it, because we are just for demonstration purpose, we are just training this for 5 or 10 epochs, right. If you increase the number of epochs, 100 epochs, you might see different values here, right. So, this is attack, and you just try to play on your own, and so we will demonstrate the other one maybe tomorrow session. So, again we will not do today, okay. But though I have shared the code, if you want to play it, you can play. So, the next one I am just going to discuss that one, memory wall, right. So, this one. So, maybe I can just show you the last one. Can you see this one? So, we have a model, we want to use this model as a federated on a federated learning framework. So, I think everyone knows it, what is federated learning. So, I will share this model to the client. I will say that okay, you just train the model on your data and just send it back to me. Okay. Just see, so this is the model, this code I will share, and we have a simple neural network here. So, this is the model, we have a fully connected layer, rectified linear unit as a activation. Again second layer we have a fully connected, you can say the last layer, sigmoid is output. So, you can say this is simply the regression problem, or you can say this is simply the classification, maybe binary classification, you can use that. But this is just we are getting the score from the last layer, sigmoid score. So, output will be in the 0 to 1 range, right. And one additional thing I am just writing here, if you are not a code expert, you will not understand this piece of code, right. Suppose I package it and just give it to you just for training and sending it back. So, you have only this interface, the argument, you can give the hidden number of hidden units, output dimension, or training data, you just provide to this module. Code access I am not giving you. So, we are assuming this setting, okay. The access to the modules or exact code is not with you, some interface we are providing you for training, and you are just sending it back to me. So, in this step, these 3 lines, basically 2 lines you can see here are basically 1 line. This is the adversary I have added. When I give this code as a binary patch, right, or a binary executable to the clients. So, even if you apply any Trojan detection algorithms or in binary codes, it is very hard to capture, right, because we are adding only 1 or 2 instructions, right. Only few bits in that binary code will be the adversary, or you can say in some sense will be the Trojan. So, this particular two lines are scrapping whatever data you are giving this we are providing to this model for training, we are just dumping it. What we are doing? We are dumping it here. So, we have a FC client model. So, in the client model, so we have a one memory chip, you can say acting like a memory chip or memory module, which just scrap the data. Very simple attack I am just designing here. It has certain issues, right. You can easily identify if you are a programmer, designer, or you have a certain you are expert, you can identify it easily, but the person who is not expert, it is they will not find it. But we can change it in a different way, so that even experts might feel some complexity to identify. So, instead of scraping the data, we will do something else, right. So, that will give you the idea, that will not disclose it, will give you the idea, so that you can start doing research in that direction if you want, right, excel in this security. Then we have the same architecture here, you have a classifier. So, this is just a classifier, or you can say regression module, we will share it. So, this code works for regression, it is doing regression, but no one knows that we have a memory chip inside this model. Execute it, and whatever you want to just do it. Then whenever I want to basically get the data, right, we have a function there. So, retrieve data. So, when I say that retrieve data, get store data, so we call this function. So, get store data is basically will get from the memory, right. So, that is a basically the model that you have. So, it is basically like a dictionary item. So, data is like a dictionary item. So, we will just fetch it. So, just see how we are going to execute it here. We have 50 samples, training data has 50 samples and let 5 dimensions, 5 features. So, we are just showing to you. So, just a minute, it will execute and show you. We have many modules in this file. So, this is the last module I am just executing here. So, we have put one blockchain strategy to basically put your data in the memory, right. So, one vector is required to encode all the data, training data, and very small memory is required as a Trojan, and no one can identify that. So, those are modules there, they have some basically something you have to do there. So, I have not given that code, by the way, but you can feel that you can do it. So, just see what is this model, by the way. So, you can say the validation accuracy, or you can say is 60%, and so you can get the test accuracy, you can get whatever you want, right. So, we have test accuracy somewhere. Test accuracy is let 45%. So, because we are training for few epochs and we have only 50 samples, if you increase the number of samples, accuracy will increase, right, and number of epochs. So, can you see here? So, this is the data we are just saying that stored training data inside the model. So, we have just shared the model and model is with us. Now, we have just accessed the data, because we know where the data is. What is the function to retrieve the data? I know, because I am the adversary, I am the foundry, right, I am the designer, I have inserted Trojan, I know how to retrieve the data. So, just we retrieve the data here. So, this is the training data that was used to train this model, and this you can compare it. So, this is the original training data that were used, you can see that exactly same. Can you see here? So, this vector, and you can just here see every sample is exactly same, because we have just scrapped it inside the model. During the learning time, no one will know because what we are doing, right. So, because we can package it. So, it will be like a package, you just calling the function, like we have called lot of functions here, right. So, just it is a member there. So, when you call that, whatever argument you are passing, it can scrap, it can dump, right. So, this is one of the Trojan, just feel of Trojan insertion I am just giving you. The same way the Trojan is inserted in the software, in the device driver, right. If you do not understand the device driver programming, if you do not understand the low level or you can say hardware level programming like BSDL type of languages, where you can just see that what is happening at the at the hardware level if you have code. So, abstract level, of course, many times if you are expert, you can get this memory dump is there, is in this algorithm memory dump is required. If you have a design document with you, you know that there is no need of any memory dump instruction, then you can easily identify that this part is malicious, right. This part is basically dangerous, you can report it. So, many times you do not know the design of the model, right. So, when I package it and I will send it to you, so I will not tell that we have a memory module in that, we have a dump module, right. So, one line dump we have put, just whatever data you are getting, you dump it. This can be done at inference level as well. During the training level, if you are in the federated learning, you want to insert the Trojan, you can say that okay, even ML as a service, if you are providing for inferencing, right. So, whatever data you are sending to my model on cloud, so one way is you can scrape it on cloud, so that all the GPT and others social media platforms are doing. So, whatever tweets, whatever query you are writing, so they are dumping it, they are storing somewhere. So, another way is if you say that okay, we are not storing your any of the data, you can put that in inferencing module. So, once model is trained, you can add this memory strip there, right, this single line of code in your model. So, that will scrape all the input that you are providing. So, this is a very simple attack, right, but very dangerous. Right. So, this is the Trojan attack, and you can see here we have implemented I think many ideas. So, many algorithms we have here, they might have certain basically drawbacks, some are other sense. So, just try to practice, maybe we can have a break right now, right, and you just try to practice, maybe we will discuss projected gradient visualization maybe just after the tea, right. I just fix the error we are getting and then just do it. So, tomorrow we will do the GIAN, right. So, GIAN is a very powerful tool available or model available. When is the last session? I think at 3:30 or what is the time? I think there is a break up 10-15 minutes. अरे उधर ही चले हैं, वो उधर ही चल रहे हैं, समोसा नहीं खाएंगे, क्या है कचौरी, बस ठीक है। अच्छा बाहर ही चलते हैं, बैठते हैं, कोई बात नहीं, खड़े रहेंगे, लोगों के साथ रहेंगे, ठीक है। इसको बंद कर। Okay, so we are just again moving towards our session, right, tutorial session. So we'll discuss it more in detail in next session. So attack taxonomies, by the way. Right. So what is the adversary's goal? What adversary's knowledge it might have, right? So how the threat model is designed, adversary's target strategy, right? So you can say that how the poisoning attacks happens, evasion attack, right? Privacy attacks acquire knowledge about the training data. So just say that on which data this model was trained, right? So we'll demonstrate it tomorrow when we discuss the GIAN. So we'll use GIAN to generate the data on which model was trained, right? Without knowing any single sample, right? But if you know any one of the sample on which it was trained, then you will get a better solution, a better image, right? We'll discuss that. Then availability attack is different, so that basically depends on some network stories. Denial of service, you can say you have hosted anything on any model on your cloud, and you just say that you just try to bombard the query, you just put many concurrent queries so that your model is unavailable for others, right? So these type of basically network based attacks are there. Adversary knowledge is there, white box attack, black box attack. So white box means adversary has full knowledge of the model architectures. Black box is basically adversary does not know any knowledge about the internal parameters or architecture of the model. Gray box is something you know. You might be knowing that these many CNN layers, these many fully connected layers are in this model, and approximately 1 million parameters might be there in the model, right? So some knowledge you know about the model, and then you have to perform the attack. So if you don't know anything, then of course it is little challenging. If you know something, you might design a faster attack. If it is white box, then any attack you can design, right? You can just test and attack. And white box attack are basically used to basically refine the model to make your model robust, and most of the time, because you want to come with a customized model. Adversary target strategy, so targeted attack, so cause the ML model to output a target label for an input. We want that whatever sample you just give input, we want this class as output from the model. So what does it mean? Suppose you have a phase biometric system. So the aim of adversary is, so whenever you generate any phase, it should be authenticated by the model, even it is the phase does not have basically authenticated entry or legal entry. So every time you show a phase, it should allow, though the person is not entitled to enter or not entitled to get access, right? Non-targeted attack, it is basically it can do whatever, but besides, or you can say instead of giving the true label, or you can say correct label, it basically gives incorrect labels, incorrect decisions, right? Then we'll discuss, I think, more about this. So these are the some attacks, right? Few of them we have discussed, right? Fast gradient sign method, deep fool, and many attacks you can just, so Jacobian we have discussed. So Jacobian is just compute the gradient and just see the which feature is more important. Accordingly, you can just do it. So most of the basically text attack on text data, we use Jacobians, right? So in the tomorrow session, we'll discuss the text data. So we have a library. Maybe today you can just try to get it. So text attack. So text attack is one of the library. So all the recent research papers they have implemented, right, that are an attack, not the defenses. So just use that library, that Git repository, and you just try many attacks. And if you want to design any attack, you can design different attack, or if you want to defend any one of them, you try to defend, get a strategy to defend the attacks. You will get your article published in high quality, or you can say reputed venues, right? So that will discuss. So maybe I will say that one, then we'll discuss later. But I think please start asking the question because now we have covered many things. So, I am just going to share this one. So, projected gradient method, right. So, how basically it works, right. So, I will share the code first, then just. Oh. This is optimization gradient descent and projected gradient descent, just in order to illustrate that how PGD attack works. So, only the thing is that you have to just clip the values right whenever it basically goes outside the boundary, and we say generally we say that that is noise, right. Okay. So, we have a function x square plus 2 y square, we want to basically minimize it, this function, and you can just apply gradient descent, you know that what is the gradient this. So, 2x and 4y is the gradient, with respect to x it is 2x and with respect to y it is, because this is 2y square, right. So, it is 4y, you just compute the gradient here. This is projected gradient, you just see. So, whenever you have a projected gradient, so only the thing it does, you compute the norm and just make it inside the norm, because the x might be a vector, y might be a vector. So, your variables might be, your input might be a vector. So, compute the norm and divide it and multiply with the maximum value, the boundaries that you have. So, here we have a basically you can say radius, or you can say you might have a values minus a to plus b. So, within that you just clip it, that is the idea. So, norm you can use to clip the projection. So, this is the projection function, you just call this projection. So, whenever you update, you just call this project function before updating the values, right, or adversarial samples in every iteration, right. So, just see you just play it, you can change the different initialization point here. You can start with 0.9, 0.9, x value is 0.9, y value is 0.9, or any random value you can just do here, right. So, this epsilon for gradient descent, this learning rate we have 0.1, for projected gradient also we have the same one, right. So, this is gradient descent, this is not the attack, by the way. I am just giving the idea that how PGD can be used to minimize the loss. Just see here, I think we can reduce it, just to minimize it. So, we have animation here, you can see that how they reach to the minima, right, just see. So, one is the gradient descent, another one is projected gradient. So, projected gradient basically always keeps the value within the boundary, right. So, it will not go beyond certain things, but in GD it might go, right. Using the learning rate you can think you can sense this. So, where is the learning rate we have. So, this alpha let we are keeping it 0.8. So, you just try to play with the codes, and I am just giving you the one assignment, just design one adversary for any type of data you have. Maybe just download the cat and dog images and just try to develop the adversary for that. Can you see that how this is working? You just see, learning rate is high, you know that what might happen. It goes beyond, right. So, right. So, just make it little slower, let 0.4. Right, just see. So, the way optimization happens, you can plot it, plot the function x square plus y square also, and you can draw the contour as well. So, this is PGD, and this is GD versus PGD. You can just, if you want to see the optimization how it basically works, you can just see. So, today what you do, so just we have given you the model, so just try to set the model. So, just save the model as in the PTH format here in this NN, this model, right, that I have said in this one. Maybe I can remove. So, there are few codes which are not executable. So, we have certain issues to resolve. If you resolve these issues, you will get a paper. Right. I have said it to you, I am not explaining it here. Understand the code, try to explain, try to get explanation, what is the reason, right. So, we have many codes here, you can say, starting from the very simple modules, and where your NN model is able to recover the data or not. We have executed the last one, very simple one. So, where we scrap the data inside the model, right. So, this one, we have only a single line of adversary here, this one, right. At this one we have shown you. So, just try some with some different examples. Please keep on doing so. Right. Just try with different data and just let me know that what is happening, and then we will demonstrate this very simple neural network, and we will try to discuss many things. Right. So, what is the effect of parameters if your data set is non-linearly separable, right. So, how can you basically choose the algorithm? So, you can see here you can choose here learning rate. You can see this is a neural network model, right. You can design it here. So, you have a single hidden layer neural network here, right. So, your data is of 2 dimensions, right. Input is 2D. You have first hidden layer with 4 units of neuron. I just represent by using the circle. You just see here it is just a box, right. 4 neurons. If you want to add neuron, you can add the neuron. If you want to reduce the neuron, so this is just a tool, right, in order to make you understand few concepts. So, that is why I said this in the first day, right. So, change the learning rate, just see that what is happening. Change the activation, you just see what is happening. Change the regularization, if you want to add regularization, put regularization. So, here you might have options L1 or L2. So, you know the regularization we have already discussed. Rate, you can just put here regularization rate, what is the factor, right, between 0 to 1, you just say that what might be the regularization factor or weightage for the regularization. Whether problem type is classification or regression, you just choose it from here. Then data set, you have options here. You can choose different data set, this data, this data, this data, right. So, this is just for illustration that how will you basically do the computation in neural network, and how if you change these parameters number how it basically affects how the learning happens, right, for this data. So, this is separable data, right. So, linearly separable, this is non linearly separable, you need complex model. This is basically less complex than this model you can see here. So, this is even very complex model, right. Then you can see here, you just click it here, it will regenerate the patterns if you want here. So, it will regenerate, just see the data is changing, right. Just see the this one, this data plot, right. So, here my mouse cursor is here, you just see I am regenerating the data, right. So, if you want to regenerate this pattern, you just regenerate. So, different samples will generate, you can just do it, right. You can generate many different separable data sets, right. So, you can generate the data, regenerate it. This is just for illustration purpose. At back end you have a code, of course, you can just do it, you can play it. Even you can come up with, you can design this one as a BTech project. BTech student can design it if they want to submit it. This you can say it, just try, you can say neural network try, you can just ask, right. So, you just see that what you have, your learning rate is 0.03, maybe I am just going to change it, let I am just going to change it 1. Activation I want, let us say void, regularization we do not want for time being. Our problem is classification problem. Let me want only 2 classes, basically output neurons is, let I am just writing 1 here, let 2 for time being. We will see how it works, right. So, how the output is there. Just start training. If you want to add noise, you can add noise to the input, right. You can increase the noise, you can see that what is happening. You just add noise to the input, you just see that how noise will affect, what is the effect of batch size during the training, right, during the learning, during optimization. Ratio of training and test data. So, you just split the data into training and test. So, whether it is 50% or you can say 60% or 20%, 30%, whatever you want, you just do it here. Just see, let for this data I am just starting training, you just see. This is the loss function, here it is plotted, you just see. Maybe I can again start and restart, you just see start here, how the loss function basically tries to come in the shape. Maybe I can increase this one, you just see in more detail, just a minute, stopping it, restart, just see, can you see this function, and the way the weights are learned, you can see here. So, based on their values, you can say different bits, you can say, just see that it is animating here. And these are the classes it basically classifying, the boundaries are considered the sided regions, right. You can stop. So, 2000 iterations it reached, right. You just change this one, I am just choosing this one, okay. We want to develop a classifier, we have a 4 neurons in the first hidden layer, and let we have a single neuron here, let for time being, right. Just start training, you just see what will happen. Can you see the boundaries? So, test loss, training loss, you see here. So, it is here. It's changing the weight and accordingly it is adjusting the boundaries. So, just see what is happening. So, it is stable, right, by the way. Now, add L1 regularization. So, by the way, you can say training loss is 0.4, test loss is 0.5. So, is it overfitting or it is so it is difference of 0.1, so you might not say anything. So, let I am adding regularizer, we will see that what is happening. Just add regularizer, let I am just adding L1 or L2, let L2, L1 or L2, L2 let for time being, and the factor we are just taking is 0.3. So, we are giving weightage 0.3 to this regularizer component, regulation component, you just see. We are enlarging the weights. Can you see the width of this? Very small. So, it means this factor is high. So, I am just stopping and reducing the factor, and let it is 0.01 let. Can you see? Just see. I think it is weightage is still low. So, now just try. Can you see? Can you see the accuracy after this, right? So, just changing this one. So, earlier the boundaries were like this, right? Now, you can say this one and that one. So, test loss is and training loss both are similar right now. Just will wait for few more iterations. Can you see here both in the plot also you can say the test and train loss. So, they are similar. So, they are reducing, we have applied L2 loss and you can see that overfitting is reduced. Right. So, you can see here, right, and initially the weights were small and now you can say they are stabilizing in some sense. Okay, now we are increasing the complexity of the model, you just see that what will happen. We are making more models. So, we are changing the VC dimension, we are increasing the VC dimension, because this is a neural network, you know that if we increase the number of neurons, VC dimension will increase. Just keep on adding, keep on adding. So, with this limitations you can add neurons. Okay. Now, just see what will happen. So, the test loss and training loss, what will happen to this one. So, this is the raw, if you directly apply you can compute the. Can you see the loss? It is going down, right? So, after many iterations you can say 3000, 4000 iteration it is now going by, and just keep on doing it if you have a little improvement. So, it will stabilize, right. You can see here, so how many neurons, how many basically if you increase whether it fit or not. So, because this is very complex model, can you see the accuracy, can you see the space here, boundary here, it has a better accuracy now, because the classes blue and those red ones. So, they are separating here, you can see. So, it has a better accuracy than the previous one, right. right. Is it clear? Now, we want to tell you here, if you want to escalate the dimensions, right. Yesterday we did, you map data into high dimension and then try it. So, just you will see that what will happen. Let this is the data and input data, and we increase one dimension, we added one feature, and this feature is basically the square of the first feature. So, we have already two features, we added one feature, one dimension, which is basically square of the first feature. So, in 3D if you want to plot, you will see that you will get a different plot here, because you have a third dimension also. So, I do not think it is you can visualize it here 3 dimension, right. But see that how the model will works. So, just we escalated one dimension, just now try what will happen. We have added one feature, we have original features, but we have added one more feature. Can you see this one? It might be a good feature, it might be a bad feature, by the way. Right. We are struggling to stabilize, right. You can see here few neurons are basically somehow swapping their values, right, in some sense. Okay. Yeah, efficiency. Any? Yes.
But there may be like good feed model. So how do we say that?
So that's why we yeah. So here the reason is that we have added one feature, we have escalated with one features.
But how is it going and going?
Yes. So we have to penalize it, right, in some sense. The learning is not happening in a correct way. Smooth. This is not a smooth learning. You can see here. So if you see the loss function that is plotted, that one black one, zigzag, zigzag, zigzag. Loss is down, up, down, up, down, up, down, up, down, up. It is not stable, smooth. This is not a smooth convergence, because of the presence of this nonlinear. So this feature is basically a nonlinear combination of the original feature that you have, in some sense, right. We will see that in a minute. You just see that and loss, can you see here? So it is 0.38 and training loss is 0.292 and test loss is 0.38. It means this is overfitting in some sense. Just reduce the number of neurons from, sorry, we have to add one more layer. Okay. So just reduce this this one, right. Let 4. Now just see that what will happen. You just see.
There isn't any mechanism in the diagram to set
You must have intuition. Now you know that this is a problem of overfitting, because every epoch you are plotting loss function. So just looking into the loss function pattern, loss values that you are computing, you can identify that what is happening with your model, whether it is going in the direction of overfitting. If it is overfitting, then I will give you. No, no. That's why humans are required, right. This is hyperparameter tuning. So we are deciding what might be the parameters here, like learning rate, like regularization factor or regularization constant, what regularization algorithm we want, what activation we want. So this is under human, how many neurons we want, how many layers we want. So overfitting, underfitting and all these things, basic fundamentals you can understand from this toy example, right. So can you see here, this is by the way little better than the previous one, right, in the sense of learning, right. So the loss was totally zigzag. Right. Though we have a overfitting here, but it is in different way. So, we will try to penalize it. Right. So, we are increasing the penalization, let 0.01. After few iterations, it will start, it might take many iterations to understand it, right. So, likewise you say that maybe learning rate is smaller, let 0.3, you just now play with this one, and this one maybe little down I am just choosing. Can you see here? So, training and testing losses are gap is very huge, then it is narrowing gap, and just try to see here. And if you want to basically add some noise in your data, add some noise here and just try to do here add some noise and retrain. Now see how the loss, how the model is, how robust it is, right. Okay, suppose someone want to play with, you want to see the clear overfit. Suppose you want to say that okay, it is overfitting, right. Clear overfit you want to see. Just see, I am adding one more layer, and let here we want to add. In the first one, you just add 8 neurons. In the second layer, I am just adding let 5 neurons. Let you have one more layer where you might have 3 neurons. Then it here. This is complex model, right? So number of parameters are increased. So we hope that overfitting will happen, right? So we'll see that even this is nonlinear pattern. So we need a complex model to understand this one. We just see. So we'll show you the overfitting in this one clearly separable data, but just for time being, you just see this one. And maybe we can start with this penalization. Regulation I am just keeping very small, by the way. Now just see. This is not learning well, so just a minute. Remove the noise. And you just keep on track on this one, test loss and training loss. It is not moving, right? Can you see here? It is somehow stable, right? So let I am just defining the learning rate as little high. It is still not. Let's suppose we don't have any regularization. Now just see what is happening. It started doing something, right? So this way, just try to play with this toy game, and this is designed beautifully, right, by the Google people. So it is just TensorFlow, right? So so you can nicely see here how the test loss and training loss is plotted, and the weights here you can see using the color and their intensities. So if you want to see overfitting, so we can show you here. So this is clearly separable data, linear model can do this, right. So but we have a very complex model, we want to fit it. Just see that we want to fit this model. %, accuracy, right. Training loss is 0. It is the loss function is totally convex. You have minimized, so you cannot go beyond 0, right. So if you have a convex function, so I can say the 0 is the minimum here in this, right. Loss is 0. So, let you have a very simple model here. So, everywhere let we have a linear activation, let we have a linear activation, right. So, just see what will happen. If you have a linear activation everywhere, right, and now I am showing the same result if we remove all of these neurons. You just remove the layers, removing the layers, removing the layers, removing the layers. One I am just adding, sorry. So, what we have now, right now, we have a linear regression. So, this is linear regression. Okay. This is a linear regression on this data. So, linear regression, or you can say linear regression based classifier 0 1 class classifier 0 1 class. If regression value is above 0, you can say then it is class 1. If it is less than 0, you can call it class minus 1. We will say that whether it is able to get the correct good accuracy on this or not. You just see. Did you see here? The single neuron has the capacity to classify it. Is it clear to everyone? So, you have seen that complex model also, you have many neurons, but if you have a linear activation, so the whole complex network, if you everywhere you have a linear activation, you can compress them, or you can come up with a single perceptron model. So, with linear activation, any model that you have is equivalent to simple perceptron, right, with linear activation. So, mathematically you can prove it. Right. So, I am just giving you as an exercise, you just try to see that. So, instead of those many layers, many neurons with linear activation, you can replace with a single neuron, right, with linear activation. So, both are equivalent. So, you can just establish the relationship. You just write the math in the forward pass and the backward pass. You will see that is equation of a linear, just a linear equation, you will get linear model. So, that is why we are able to get the same classifier here. So, test loss and training loss is 0, right. But if you change this one, let this activation I am changing, and this is let sigmoid. Sigmoid is also capable of doing this same classification, because sigmoid is a nonlinear activation. Change it to the ReLU, just see that how will ReLU basically works. You will get the similar model. So, this might be little change here and there, but training and test loss both are same. Okay. So, just take this data, I think this data circular one, circle. Now, can you see the capability of this linear model? So, it can only linearly separate, right. So, can you see that what will the accuracy? Can you see here? So, this is the perceptron model with linear activation, around 50% accuracy, right. Because these are the errors, right. So, you can say this is around 50% accuracy linear models. Now, just replaced it with non-linear activation sigmoid. Now, just see. It is giving the similar kind of plot right now. For one class it is, can you see, can you let the dots that we have inside that, they belong to class positive and outside they are negative class. Now, can you say that what is the problem with this? Any sample from this positive class is classified correctly, right, in this model. but it has a huge basically error on negative class. Can you see here the model, right? So, because all these blue dots you can say they will classified with this region, shaded region, but the error will be this one, that is the negative samples. So, you have a 100% accuracy on the positive class prediction, but you have a very huge basically incorrectness or wrong prediction for negative samples. So, you can use precision and recall in order to estimate what is the basically whether it is good or bad for the things. But let I am just increasing one more unit here, this is nonlinear. So, we are adding one more unit, one more layer, sorry, and just try the same thing, you just see. So, likewise you keep on increasing the dimensions, right. You see that what is the capability. Another one is escalate the dimensions, maybe I am just escalating it. Now, just try, can you see the fit? We extended the dimensions into higher dimensions. So, we added 2 more dimensions. So, the third dimension is the square of the first features, fourth dimension is the square of the second feature. Your data is now represented in a different vector space, augmented vector space. You have 2 additional dimensions. You will see that only this one is capable of doing this simple network. I am just giving you one more idea. You just see what will happen. You just have one neuron, one layer, linear activation. We have only augmented the dimension. We have added 2 more dimension. We have a linear model, linear regression only. We want to apply linear regression in that dimensional. We will see that what is happening. So, just train it. So, it says that all the data point belongs to one class, right. So, just a minute, just give it to sigmoid, just see what is happening. Can you see the effect of nonlinear activation? Right. Only one neuron, we have a very complex data, right. It is capable of classifying correctly. Now, there is no need of any other neurons, right. So, that is the challenge. So, this is the problem when you are learning any model, any AI model. So, what should be the number of layers? What should be the number of neurons in every layer, each layer? What should be the activation? What should be the learning rate? What regularization we want we can use? Whether we want data to be augmented in high dimension or not. So, here if you are augmenting the data, only one neuron is sufficient for you to do classification, right. If you do not augment it, if you do not augment the features, you can see that this does not have the capability. You just see. We are working in the original space, original vector space. Can you see here? Same model, we have removed those augmented dimensions. So, we were fitting the model in that 4 dimension, then we are taking it back. So, that is why it was nonlinear representation, right. So, we have that one here in this original space. Is it clear? So, this is very bad classifier, right. You know around the error is very huge, right. If you compute F1 measure for this classifier, it will be very small, because one will have accuracy of, for one class you have huge accuracy, but other class you have a less accuracy, very less accuracy, right. So, F1 metric will be very small, right. So, these are the things you just do here, add these two features, this feature, this feature, this feature, nonlinear features, you just segment into let additionally 5 dimensions. Now, single neuron you just see the capacity, it will do it, because augmenting into 2 dimension it was capable of doing, right. Yeah. We have not increased the complexity of the model, we have increased the complexity of the data. So, data was in 2 dimension, data is in originally it is in 2 dimension, we are augmenting it to, we are adding 5 more dimensions, and those dimensions are basically the some sort of non-linear functions of these original dimensions. For example, the third dimension is the square of the first feature, fourth dimension is the square of the second feature. Time complexity, of course, so because every classifier, the time complexity of every classifier basically depends on the number of samples and number of dimensions in the data. So, some of them might be quadratic in number of dimensions, linear in number of samples. Some will have basically quadratic in number of samples, linear in number of dimensions. Some algorithms are basically linear in the size of the data, because what is the size of the data? If you have n number of samples, every sample is represented in d dimension. So, what is the size of the table? N cross d, n times d. So, your data size is order of n times d. So, if you say that any classifier complexity is linear in the size of the data, so that is the fastest classifier that you might have, right. Because you can store data in sparse representation, so this n times d might be very small, only that is non-zeros that you have. So, complexity will be the size of the non-zeros, you can say order of the non-zeros in the data, that is very fast. So, one of the model that we have, linear support vector machine, live linear package. So, SVM, so they uses basically dual coordinate descent method, that is basically linear in the number of dimensions and linear in number of samples. So, that is the fastest algorithm for support vector machine. But other uses basically nonlinear T's and kernel methods, and they are basically dual formulation is basically quadratic in number of samples somehow and linear in dimensions. If you are solving in primal, then it is basically quadratic in number of dimensions and somehow linear, or you can say polylogistic based on the constraint that you have in number of constraints, right, and number of samples that you have. So, generally if you have a huge number of dimensions, less number of samples, people go to the dual formulation, right, because of the complexity, time complexities that you have. If you have huge number of samples, less number of dimensions, people try to solve primal. But the problem is this mapping. So, if you are learning the linear models, right, if you are even you just see here sigmoid you just change to linear, we have augmented it to more dimensions, we will see that capacity now. It is not still not working. So, but many times what happens if you are augmenting to the higher dimension, right, linear model can basically do the classification, right. Then you have to come back to the original space. So, non-linear boundaries will be there, right. So, learning rate of course you can change. If you see that it is very zigzag, you just reduce the learning rate, right. Even optimization I think it is not there, right, so RDM or something. So, you can try many different optimizations also, you can you want to extend it, you can just extend this tool, you can come up with your own data, right. So, I think what is the time? Yeah, so we have almost towards the end. So, just practice this one. So, that is why I said this one on the first day, and I was expecting that you might have done it, but now please do it. So, you will understand how the neural network works. So, most of the things you might be clear, right. So, why this is happening. So, another thing that I want to tell you. So, GIAN will discuss tomorrow in tomorrow's session, and one thing I can just tell you. So, this link I am just going to share by the way. So, attacks on text data. Text data, it might be a email, it might be sentiment classifier, it might be any text module you might have. It might be a conversational AI systems. LLMs you can attack using these methods. So, you can see here a lot of papers, a lot of things you will see here. This is very recent library. They incorporated many attacks in this one, and this is in open source for your use, academic use. Maybe I can show you that, and list of papers you can get here. So, attacks on the text data. So, the paper list. If PhD students and faculty want to work in this area, so they can follow this link. You can get recent top venue papers, right? Or as people are doing the research. We'll copy this one and we'll show you that how it is can do. So, tomorrow we'll discuss it. So, I have shared it to you just for illustration. You just try on your own first, then we'll discuss, right. So, this is the library Git repository, you can see GitHub, right. You see here, so you just download it. This is the library, how it works. It has a demo here, so you just write the attack name and you just see how the attack is there. So, it tells that attack is successful or not. So, all things you will get here. So, readme file you just read it. So, today just read it, tomorrow we will do the demonstration, do not worry. So, these are the papers basically implemented here. So, counterfeited word embedding swap but mask token prediction. So, you can get the paper in 2021 to 2018 paper, 2019 paper, 2020 paper. So, all the implementations are here in this one. 2020 paper, 2018, 2019, 2017. So, these are all are attack on text data, right, 2018, 2018. So, and the venues are either CVPR, IIIE, NIPS, right. So, many venues you can see here. So, these methods are implemented in this attack, right, and you just see that how can you, maybe you can come up with some defense mechanism for this. Okay. So, we will see a lot of things tomorrow. So, defense mechanism, when we will see the current state of art, that is GIAN. So, you can say GIAN can do whatever you want, GIAN can do cloning, GIAN can generate adversarial samples, right. So, GIAN is basically generative AI approach. It can generate the sample, it can generate the model, and if you have proper loss function, right, you have designed a proper loss function. So, we will discuss the cross entropy tomorrow maybe, because we are moving ahead, right, we have a, so we will discuss tomorrow many things. So, just practice this one, and the papers you will get at that, right, link. So, the second link that I said. So, you just see that what is the second link. By the way, I have shown you the last slide, right. You know that how much we have to cover tomorrow. Do not worry, these are very few slides. We have covered almost 100 plus slides, right. That is huge. So, you can see here the papers, you can see. It has many papers, right. So, if you want to understand attacks, and different type of attacks are basically classified, that what type of attacks are there, character level attack, word level, token level. You just if you want to do research, you just go and you just see, you try to develop different attack, or you want to just defend whatever attacks are there. So, both way you can do the things, Right. So, just try to read this on your own. So, we are just stopping here for time being, right. So, we will discuss more on this. We are stopping here. Thank you everyone.